coordinator. In 2010, moved to ULIC Supercomputer Center, where he works within the Application Support Division. His work is primarily focused within the Link Scheme 2 project, helping to develop a virtual research community in computational science in the Eastern Mediterranean region. We're going to continue till 12:20, 12:25. I'll be back here. Please, then, we're going to go very quickly downstairs to lunch. We have to be at the bus at 1 o'clock. Other than that, Alan is going to be running it, okay?
Thanks very much.
All right.
I'll just give myself a little bit of timing because I have quite a bit to get through this morning, and we just shaved 15 minutes off what I had. So maybe for this presentation I'll be quite quick and just give you a quick overview, and I'd like to spend a little bit of time in our hands-on. So I'll time myself for 45 on this, I think. They should have been. They were there originally. I got them to re-upload them this morning. We need Hank then for that. We need because Audrey did that.
Trace analysis. Just upload it to Dropbox now and give us the link. Do you need Hank?
Yeah, Hank. Yeah, please, yeah. Because Audrey has all the files. She told me that she.
The parallel performance engineering is up there. You have to click on the right where it's to the right of where it says slides. There's two PDFs. One's called engineering, and that's his presentation.
Engineering is the first one, yeah.
Right,
yeah.
that's up there.
So it's called engineering. This presentation is engineering. The next one is Skalaska. It's called, I think.
Yeah.
Yeah?
They're both there.
They are there. Okay. Okay. Sorry, I just want to start my timer here so I have an idea of where we are.
Oh.
Do they work? Yeah. Okay. So this presentation is actually from a group. ULIC is a partner in that group. It's called the Virtual Institute for High Productivity Supercomputing. This presentation is kind of an introduction to the ideas behind some of the tools that they create within that workshop.
Could I ask you to sort of stay around this area so I can actually see you, because we've got the whole thing in the frame.
Yeah.
Not in front of the thing, but just next to
I got you. My name is Alan Akash. I've already been introduced. The content for this presentation I got from other people a lot of whom were in my own institute, and then there's some other people from companies like Cray as well who've been involved. VIHBS has quite a few partners based all over the world, and they work together trying to developing tools that are used to kind of do high productivity supercomputing, so to help people to create efficient applications. The whole issue of performance is a very old problem. It's been around basically since computers were first invented. This is the difference engine. It was created in the early 1800s, 1820 something like that. And one of a quote from the time from Charles Babbage, who created the machine, is the most constant difficulty in contriving the engine has arisen from the desire to reduce the time in which the calculations were executed to the shortest which is possible. And that basically hasn't changed. Everybody, once you get a machine that's capable of doing something, you want to do it faster and faster, and you typically always want to push the boundaries of what the machine is actually capable of doing. So what we want to do is an old thing. The other thing these days that people say is that the free lunch is over. Moore's law still exists, it's still in charge, but we've run into some walls that we can't really get past. And one of them is the clock speed. And in fact, the three of them are all really related. There's this clock speed, the power, and the performance per clock tick. The whole problem is that we can't increase the frequency anymore, and actually we've come to the stage where we actually reduce the frequency on the chips because it costs too much power to keep them at that level. Right? So basically we've stopped increasing the power of the actual chips, and instead we've gone to parallelization. Right? So we put multiple cores on the chips, and that's only going to get more pronounced. We already see it in these GPUs and in the Xeon Phis and things like that, where we have more and more cores on a single piece of silicon. The issue, and so now we're at the stage where the performance gains are only going to come through increased parallelism. And that creates problems for us, because that means that the optimization of applications is actually much more difficult. It's not just a case of give me a faster chip and my application will run faster. Because of the way that this performance improvement is being achieved, our optimization is through a process of utilizing these parallel processors, and that's not so easy to do. We also have increased application complexity. So we're no longer doing a single area of physics or something like that. You can have whole climate models and things where you have multi-physics involved. Things are happening at multiple scales, and that's where you have graphs and things like that, where you have different density of points at different places. And then, of course, the machines get much more complex in general. And because they get so large, we're on the scale of talking about millions of processors these days. We typically have hierarchical networks, which means there's, you're closely connected to your nearest neighbor, but then as you move farther away, the times to access those further away machines get longer and longer. So you have networks on multiple levels. The same has been true for memory for a long time, and it's increasingly so. You have memory that's close and that's far away, and you have to take into account that these perform at different levels. The other thing is we have more and more CPUs, of course, and then how do you actually utilize them in an efficient manner? And of course, the thing is that every time we double the scale, every time we get to a faster machine, it's always a new bottleneck. So before it was, it really has just changed. The paradigm at the moment is with this parallelism just makes applications much more difficult to create in an efficient manner. But every time there's an increase in performance, there's always something new that's your new problem. On the scale of the machines at the moment, one of the big ones is actually just moving the data to the processors. So now the processors are capable of doing things very quickly, but the architecture underneath that level is not so competent. And really, how fast you can go depends on the problem that you have. So typically, like the area that I'm from, Lattice QCD, your bottleneck is actually moving the data from memory space into the processor. An example application that they show on these slides is from Aachen. It's about half hour away from Jülich, where we are. It's developed by a group there, the CATS community. It's basically fluid flow. It's some kind of blood pump. It has more than 40,000 lines of code inside, and it does some blood pumping on some high dynamic flow simulations. So it's fluid dynamics, and basically this is quite old now, it's from 2007, but back in 2007 they had created this blue gene, very, very highly parallel architecture, and they wanted to see how this application scaled on a machine. And so basically they took the number of processes and they doubled them and they doubled them again and doubled and doubled, and they looked at how much work they could get done in that time. And you can see that basically they split these lines into the total time and then the time taken on communication and synchronization and the waiting time. And you can see that the larger the number of processes that they got, the more time they spent basically wasting their time just waiting around for things to happen, right? And so there's been a lot of focus in the last few years has been how do you minimize the impact of this parallelization? Because of course you are going to be faced with these issues where there's synchronization and there's going to have to be waiting and things like that. So how do you actually minimize the impact? And you can see in this case that the impact was actually huge. From 256 to 4,000, it's a factor of 16. But actually the performance improvement is only a factor of 8. Right? So basically our scaling is very poor. It's at the level of 50%. So it's much below, far below what we would actually want to achieve. So what actually affects these performance factors? Well, there are a couple of things that you should probably take into account. The very most basic one is the algorithm. These are kind of sequential things you have to think about before you talk about your parallelism. The first thing you want to do is choose the right algorithm. That makes a huge difference. Algorithm development is happening all the time, and if you choose to do something, if you choose to begin a project, you should really try and make sure that you're using the most up-to-date algorithm, because there is development all the time, and typically when there's a big development in algorithms, it means performance improvements on the orders of magnitude, right? So 10 times, 100 times, right? So if you have an application, you can hope to, if you use the general tools, you can hope to improve things by, say, you'd be lucky to get a factor of 10. But if you change the algorithm and the whole mathematical approach to the problem, you can get factors of 100 improvement. So really you have to make sure, the first thing you do is make sure that you're using the right algorithm. The next step then would be to make sure that you're using the right compiler, right? Make sure you're using an optimizing compiler, something that works really well on your code. And the only way to know that you're doing that properly is to actually try things out. Typically, I would say that you talk to people like me. I do user support at Jülich Supercomputing Center, and we can give you some hints about what you should do with the compiler, but there's always a little bit more. The question is, what's the point where it's not worth it anymore? I mean, typically, with your first little bit of effort, you might get significant performance improvement. But after that, it's pretty minimal, and maybe there's a point in time where it's not worth going too far into it. But the compilers are very useful. They actually can give you a lot of useful information about how to help them to optimize your code, and so that there are a lot of things you can use there. The other things are cache and memory. This stuff is really complicated these days because you have these multi-core architectures and they have different cache levels, and you've got this you have cache coherency and all these factors floating around that you don't really control, because typically the compiler is doing all this work underneath. So nothing is very exposed to you, this whole cache hierarchy. Well, it's exposed to you, you can see it, but how it actually operates underneath the hood is not exposed to you. So it's very tough. There's limited tool support, and so basically your hope here is that the compiler just gets it right. Right? So it's something that definitely impacts you, but you don't have too much control over it. The one that gets forgotten an awful lot is the input and output. At a certain scale, it's not a problem, right? When we're talking about using 100 cores or something like that, then I/O is probably not going to be a problem for you. When you get to a scale of tens of thousands and hundreds of thousands and even millions of cores, it actually becomes a serious issue. And we'll talk about it a little tomorrow. I'll show you what the impact of that can be, and I'll show you how to get around it a little bit. The other thing are the parallel factors, and the ones that we're really interested in. One of those is how do you actually decompose your problem. This has performance impacts for you, because it controls how much messaging you do and how you actually how your problem is actually decomposed and how you can do the processing itself. So this is one of the first factors that you hit, and then of course is the communication itself. That's a parallel factor, obviously, because you have to pass information around. When you do partitioning, you have to create halos or extra information and things like that, and that has to be passed around from processor to processor. And then we have multi-threading, so then it's OpenMP or other libraries like that that come in as well, and so you have another factor. And the factor in here, the one that we're kind of going to focus on today is synchronization and locking. The idea that at some point the processors are going to have to know where they are in relation to each other, right? And so there's some synchronization involved. And because of that synchronization, then there's probably locking. There's some point where they have to wait and stop and then move on forward once everybody reaches the point that we expect. In this case, things are more or less understood, right? There's really good tools out there to help you with this stuff, and that's what we're going to look at today. So basically, for the tuning stuff, just the basics that we're going to go through today is, the idea is that successful engineering is a combination of different things. The first one is picking the right algorithm, using libraries like we saw this morning. The next one is another kind of basic one, compiler flags and directives, picking the right ones, checking that your code actually works once you use some of these compiler flags, making sure it's faster, and then picking the one that suits you best. And of course, you're just going to have to think. It's not a problem where you put in code one end and you get the optimized one out the other side. It involves you understanding some things as well, and sometimes that's not so easy. And that's why we say measurement is better than guessing, right? So you think you know what the problem is with your code. That may be true, but sometimes it's not true, all right? And rather than think you're right, you should actually measure to see if you are correct, right? You use measurement to determine the performance bottlenecks. And then once you have those bottlenecks, you can compare alternatives. You can look at different approaches, you can implement them, and then you can compare and see, did it improve, did it not improve, what way should I go? So basically these things allow you to validate your decisions. You see something, you try and improve it, you implement it, you measure it, and then you see if it has really improved, and then these things validate the decisions that you tried to make to optimize your code. And the thing is, this is a cyclical process, so you have to do this after every step. So basically, it's not just that you go in once, you measure something, then you go, this is my path that I'm going to take to optimize my code. I do it, and then I don't check, right? And I just go away and say I'm finished. But things can change, right? So if in the first case your performance bottleneck is actually the thing inside your code, some little routine in the middle, right? And then you figure out something, and then you improve that, right? So now that's considered optimal. You're very happy with how that came out, and then you rerun the code, and you see that now MPI is your bottleneck. So now you have to go back and see, well, why is MPI my bottleneck? You find out that, you improve that, and then that's fine. You move on to the next step, and then you see that you now have another bottleneck, which is maybe OpenMP, or maybe you're back to some problem in your code itself that you could improve further. So it's a cyclical process that you have to go through in each case. The thing about it is, you should also know when to stop, right? So at some point, you should be relatively satisfied, and don't worry about small inefficiencies, okay? Or small efficiencies. Premature optimization is the root of all evil. The point of this statement is really more along the lines of that don't optimize until you know you're correct, basically. So don't worry about all this optimization stuff until you have a working application first. The idea is it's easier to optimize a slow, correct program than to debug a fast, incorrect one. Right? So the first thing is to get the answer right. And then you can worry about, there's all these tools out there to help you to optimize your code, but the first thing is to get the answer correct in the first place. And of course, nobody cares how fast you can commute a wrong answer. Right? Nobody cares about wrong answers. So if we look at the workflow that we have to go through in this thing, the first thing to do is to prepare the application somehow. Maybe with symbols, but that's a simple compiler command that you can give. You can insert extra code in there to say to make it look at particular areas. Then you do some kind of measurement. You collect the data that's relevant at some particular point in time, so that you can do your performance analysis. And then we actually do the analysis. We calculate some metrics, some things that help us make decisions, and then we identify the areas that we're interested in. We kind of present those results in some kind of understandable way, something that we can actually work on and try and figure a solution from. And then once we've done that, we optimize our application. We make some modifications. The idea to reduce, to implement, to affect these performance metrics and hopefully improve things. And then we just go back to the start and do it all over again. What we want to remember is this 80-20 rule. Typically, programs spend most of the time in a certain region of an application. It's about 80% in about 20% of the code, okay? So programmers, again, when they're doing the optimization, they spend about 20% of their time trying to get 80% of the total speed up possible. And then that's probably enough, right? There's no need to push things to the absolute limit, okay? So really, you should do this initial optimization effort, and then you should know when to stop. Then, you know, if you're happy with, if you've gotten significant improvement, and if the next level of improvement is going to take a lot of effort on your part, it may not be worth it. Your time is valuable too. But you need to be able to recognize when that's the case. And of course, don't waste your time optimizing something that doesn't matter, okay? If you have this case where you're 80% in one area and 20% in the other, then you optimize the 80% area and you forget about the 20%. That's not where your problems are, right? If the code is spending all its time in this 80%, that's what you need to worry about, not the 20%. Make the common case fast. And another computer scientist, another useful quote: if you optimize everything, you will always be unhappy, okay? It will never be perfect, right? And you can waste your time for a very long time. And it's not worth it for you. I mean, at some point, you want results from your applications, so don't spend all your time optimizing. That's not useful, you're all scientists. This is not useful for you. At some point, you should be satisfied. And if you're not, you should seek help. If you need help with something, there's people out there to help you, like these VIHPS people. So the metrics of performance. So what can actually be measured when you use these tools? Well, there can be a count of how often an event occurs. For example, you can count the number of MPI point-to-point messages within the application. You can measure a time interval, right? You can see the duration of an interval. How much time was spent between the MPI send and the MPI receive? How much time was spent between calling this function and calling that function? How much time between entering this function and exiting that function? And then you can also have the size of some parameter. So how many bytes were sent in a particular call, something like that. And from these you can have some derived metrics. You can calculate rates and throughput, and they're pretty useful to do normalization, to get an idea of what are useful numbers here. So you can have an idea of scale. So some examples of the metrics that are used are the execution time, of course, like how long something is executing for, how many function calls there are inside, so how many times do you call a particular function, what are the CPU cycles per instruction that you get, and then the number that you hear about a lot, flops, floating point operations executed per second. The problem with flops is it's open to a lot of interpretation. What does that mean? Does that mean maths operations? Does it mean hardware operations? Does it mean hardware instructions? Are we talking about 32-bit or 64-bit? There's lots of flexibility in how you interpret flops, and vendors use that all the time when they're selling equipment. So basically, on the execution time side of things, there are a couple of things that you're interested in. Probably one, if you're developing applications, the one you care about the most is the wall clock time. How much time does it take for me to get my answer? That includes everything. It includes the waiting time, which might be for I/O, might be for memory, might be for communication. In a case where you're sharing the time with other people, it also includes the time where somebody else is using the machine. The CPU time then is actually the time spent by the CPU to execute the application. It does not include the time where it was context switched, so where basically it got swapped out because somebody something else had to do some work. So it doesn't include, and it also doesn't include the inherent waiting time. So basically when it's waiting for I/O, when it's waiting something from the disk or something like that. And there's a problem with the idea of portability in this case. What is user time, what is system time? It depends on the system that you're talking about, what the operating system is, things like that. So the execution time is a bit non-deterministic as well. The thing is, it can vary, right, from time to time for a number of reasons. The disks might be busy, so the underlying storage hardware might be busy doing something else, or at some stage the processor may have to switch something out to check the time or something like that. So things happen when an application is executing. So each time things can change a little bit, and so it's a bit non-deterministic, which we recommend that you try and do a couple of runs and make sure you're getting relatively consistent results. And then, of course, there's the idea of inclusive and exclusive values. So inclusive is where you can capture everything in a certain region and talk about it as a whole. And exclusive is where you can subdivide the information into sub-pieces. So if you look at a routine like this, where we just have a simple function call, all it does is declare a variable, do something with it, call a function, do something else, and then return it. So the inclusive time would be everything from beginning to end. The exclusive time would be everything where we do something that's exclusive to this function, right? So the beginning with the declarations and the operation on A, and at the end. But this further function call, that's measured somewhere else, basically. So in the exclusive case, it can't be subdivided any further. Bar has its own measurement, and the exclusive case foo this is all the stuff that happens exclusively within foo. And then we can classify the measurement techniques. So the question is, like, how do you actually approach this? So how are performance measurements triggered? How do you do it? There are two techniques that are typically used. One of them is sampling, where basically you just stop the code and you look at things at a particular point in time, and then you repeat that. Stop, look, regularly throughout the thing. And the other one is code instrumentation, where you actually insert special pieces of code to say, hey, capture this event, capture that event, capture this, capture that, and record things that way. The next one is, how is performance data recorded? So how do we actually collect the information? Once we've done the profiling, can we have some kind of summarization? And if we want more detailed information, what about tracing? And then how is the performance data analyzed? You can do it online as the application is running, or you can do it after the application has actually died. So we're going to look at these one at a time. And the first one up is these performance measurements and how do you trigger them. We'll look at sampling first. So sampling basically means that we come in and we have these routines, main, and it just calls foo, who calls itself. So, and then it basically flip-flops around in between the routines as it's executing over time. And in the case of sampling then, the running program is periodically interrupted to take a measurement. So that can happen due to some kind of timer interrupt, some signal to the operating system to tell it to do it, or maybe you have some hardware event that you're counting and it has an overflow, and that overflow will trigger the interruption. Then you have some service routine when that interruption happens that takes a look at the stack at that time and then maps it back to where it was in the code at that time using some symbol tables. So basically, we do an interruption at time 1, and this one is the regular case where we just interrupt periodically and see where the code is at a particular time. So at T1 it's in main, at T2 it's in foo for 0, at T5 it's back in foo at 0, T6 it's in foo for 2, so on. Right, and we just do that regularly. And at the end we have a measurement from this information. We collect all this information together and we got some kind of measurement. So we take a statistical inference of what the program is doing. So we don't exactly know what the program is doing, but we have an idea because we look at it at various moments in time. The problem with this is it's not very detailed on something that's highly volatile, something that changes a lot. And it also requires long-running applications. And the longer the application runs, the more statistics you have, the more you know about how it operates. On the plus side, it works with unmodified executables, which is very useful. Right? So it means that you don't have to do anything to your code, it should just work. Right? The alternative then is to do instrumentation. Now in the case of instrumentation, we have the same running application, but this time we insert special code. So we insert measurement code so that every event of interest is actually captured directly. It can be done in a number of ways, but the idea here is that basically when we enter main, we say, hey, capture the fact that we entered main. Before we leave, we say, we're about to leave main, capture this too. And then basically we do the same inside foo. We say, hey, we're entering foo, and then we're leaving foo. We capture all these events every time they happen. So in this case, our collection of statistics looks a little bit different because we do it at every significant event. Okay, all the way along, every time we see something that we're interested in, we capture it. It has an advantage in that you have much more detailed information. You know exactly what went on during the runtime of the application. But it also has some significant disadvantages. You need to pre-process the source code. And that sometimes can be non-trivial. I mean, the tools are out there to help you to do that. Sometimes they work very well and it has no real impact on you. Other times they can have a significant impact and you have to be aware of what the downsides of these things are. Sometimes you can have, and one of the big ones is that the fact that it can introduce a lot of overhead. So if we call these routines, for example, if we call foo many times, and it does almost very little work, right? So we're continuously calling routines. There's a lot of overhead from the fact that we're just simply recording these events, enter, leave, over and over again, and that brings a lot of overhead as well. So we need to be aware that that happens, and there are techniques for removing that overhead, which we'll go through in the hands-on. So on the instrumentation side, you can do static instrumentation, where the program is instrumented prior to the execution. You can also do dynamic instrumentation, where it's instrumented at runtime. Static instrumentation is the one we'll do today, and dynamic we actually will do it tomorrow as well, but it'll be kind of behind the scenes. You won't really know what's happening. So the thing about dynamic instrumentation is basically what it does is interrupt function calls that go to shared libraries. So basically it sees when you try and go away from the application to a shared library, and it interrupts that call and wraps it around, and then brings the function call back. So it can kind of capture these events that happen. But basically it means the code is inserted, either manually or automatically or something like that. In our case, we'll be doing this kind of pre-processor translation thing. It can also be done by a compiler. Some of the compilers have little flags that allow you to do this. You can link it against a pre-instrumented library at runtime. So instead of using your own MPI, or, well, not MPI, maybe it's a bad choice, but some instrumented library instead of the typical library that you use. And then, of course, there are some tools out there that will actually do a binary rewrite as well. So basically, they'll take the binary, they'll look at it, and they'll rewrite it in such a way that code is also inserted inside to do this instrumentation. There are some critical issues there. The accuracy is one of them. Because you're introducing this code, it has an impact, right? So there's this intrusion overhead. The measurement itself takes some time, and of course that's going to affect your performance, right? The idea of the development of the tools within this group is that that impact is as low as it possibly can be. And then of course there's other factors that come in, which is this kind of perturbation. Really, the big place that this probably impacts is in the memory access. Your memory access pattern will change a little bit because you have some variables that are associated with the measurement tool. Now, depending how much that really impacts you, it's hard to say. It depends on the application. But it could have a significant impact, and it's something you should be aware of. The basic idea is that the fact that you're doing measurement means that you're going to alter the behavior of the program somehow. The other thing is the granularity. You want to think about how many measurements do you really need, and how much information or processing should be done between each measurement. There's always a trade-off. This instrumentation approach is accurate, right? But then you don't want to impact the data so much that even though it's there, it's not actually very expressive of your real life usage of an application. So you have to be careful here, and you have to take into account that there are impacts involved, and you need to be able to quantify them somehow. So we're back to our three things, and now we're going to focus on the second one here, which is how do we actually record the data and how do we look at it. We can do a kind of, in our case, in the Scholastic case that we're going to go through, we do runtime summarization. So basically, we look at all the aggregated information, and then we just take some statistics. We look at the totals, we look at maximum and minima, things like that, and we try and infer some things from that. They're very useful for some measurements, for the times in general, for the counts, the function calls and things like that, how many bytes were transferred, and there's also hardware counters that we can look at. And then you can also look at things like the functions themselves, and the blocks and the loops and other things like that, and the processes and the threads, what actually happens on particular processes and on threads coming from a certain process. You'll also be able to look at that information. So the profile basically is a summarization of events over the execution interval. There are different kinds of profiles. There's a flat profile, which just shows the distribution of metrics for a particular routine or a particular instrumented region. The actual calling context, so when it actually happened, is not taken into account. Probably more useful, and what we'll kind of look at a little bit today, is the call path profile. It shows that the distribution of metrics on each call path. Sometimes these are they're only distinguished to a certain level. It depends on the purpose. And then we have special purpose profiles, where you want to focus on particular things. And these might be MPI calls, or it might be related to OpenMP or something like that. And in this case, then you would like to be able to compare processes or compare threads. Processes in the case of MPI and threads in the case of OpenMP, and see how much work they're doing relative to each other. You want them all to be busy all the time. Tracing is the other thing that we're interested in. The idea with tracing is that we record information about significant events during the execution of the program. So when we enter a region, when we leave it, if that's a function or a loop or whatever, especially when we send and receive a message. And we can save information in an event record. So the event record would have information like when did it happen, the timestamp, where did it happen, and what kind of event was it. And there might be some event-specific information. Maybe it was within a particular communicator, who was the sender, who was the receiver, if we're talking about MPI or something like that. And then we abstract things a little bit from the level of defined events. So we can look at particular events and group them together and look at them like that. So an event trace then is chronologically ordered and just in a sequence of event records. So you can see when particular things happened. So we can have a look at an event trace in the case of this example where we've got two routines, process A and process B. One case, A is going to send something to B and B is going to receive something from A. So we want to trace this event. We introduce some new code. We say we're entering into this routine foo. We're about to send some information to B. We're exiting from foo. On the other side, we're entering process B. We're entering bar. We've received something from A. So this happens. We record this after it's actually happened, and then we exit from the routine. So we're monitoring this. The first thing we do is synchronize our clocks, and that's one of the hard things to actually do really, really well. You want to synchronize our clocks so everybody's talking about the same point in time. And then we do the event trace. We say at timestamp 58 we entered, at 62 we send, at 64 we exited. On processor B then at 60 we entered, at 68 we received, at 69 we exited. So we take that information then and we can unify them. For the actual functions themselves, we can unify them into their function calls. And for the events, we can unify them according to time. So we have this global trace view. So we know exactly what happened in our time order, then. So we just collect that information into a global trace view. So what are the advantages and disadvantages of tracing versus profiling? The advantage of tracing is that you have very, very detailed information. They preserve the temporal and the spatial relationships, so you know when and where things happened among individual events. So it gives you all the context of something. It allows you to reconstruct the dynamic behavior of the application at any level. And it's the most general measurement technique. It provides everything you need to know. And it can be so basically you can reconstruct the whole profile from the event traces. It has some pretty big disadvantages. The traces can very quickly become extremely large. You can imagine how much data you're collecting with this. And so, especially when you get to very large machines and numbers of cores, these traces become absolutely enormous. Right? So it's something you have to be very, very wary of. And once you start thinking about doing tracing, you're talking about very, very large file sizes. The other disadvantage is that actually writing the events to a file, it costs you, right? It's going to cause some perturbation to your application. And you have to know that that's going to happen. And, of course, the biggest disadvantage is that actually writing the software to do this is very complicated. There are lots of things you need to worry about. The big ones are the actual buffering of the events. How do you store the events when the application is running? And then one of the big ones is actually how do you synchronize the clocks on so many processes? We're talking about millions of processes at some point. So how do you actually synchronize those clocks? We're back to our 3 and we're on to the last one, which is how do we analyze this performance data? We can do it online. So performance data is processed during the measurement run. We can do some kind of local profile aggregation. We can do some sophisticated inter-process analysis. We can piggyback on messages and things like that. That's what Scholastica does. It kind of hides things inside the messages that are being sent anyway. And then we can have a hierarchical network of agents that are analyzing different things. Inter-process analysis often involves application steering. So basically, you interfere with the application a little bit because you're only interested in the performance information, not in the actual result. So you can move things around a little bit and not have to worry about it too much. And so you can reconfigure things that way. You can also do post-mortem analysis. That's more or less what we'll be doing today. The performance data is stored at the end of a measurement run, and we do some data analysis on that afterwards. This allows us to do some kind of automatic search for bottlenecks. We can do visual trace analysis, and then we can calculate some statistics and interpret that information. So another example again, we're back to our trace routine here. So we can visualize this on a trace if we wanted to. The first thing we do, we can see we enter A at 58 and we leave, and we exit at 64. Well, they're actually, sorry, this is main that's coming up here first. So main was obviously running for the whole thing. And then this is A, just onto the trace, and then B also onto the trace, so where we enter and where we exit. And then we have the send and receive at a certain point in time, so we can just draw our arrow. That's basically what a trace file will look like. It'll be pictures like this, where you have things happening over a period of time, and that there's little arrows saying that there was a message passed at this point. And so you have, and the different functions will have different colors, and so to help you distinguish them more easily. That's basically what a trace file will look like. The big thing to kind of come back to is that there's no single solution that will do everything for you when it comes to performance analysis. You need different tools for different jobs. And so basically the example they like to use in the VIHPS is like working in your garden or something. You can't do everything with a spade. At some point you're going to need some other tools to do the various jobs that you have in your garden. And then if you have a really big garden, then these small tools are no longer big enough, and you need things that work at a very large scale, because that's the point you've come to when you've got a garden of that size. And when you're using these kind of very large tools, you're going to need help. And that's why an institute like this VIHPS exists. Because if you manage to get to the scale where you have to use the heavy machinery, then you're probably going to need some help, and they're the people who have the experience. And they're pretty good at being helpful at these things. So the point is that you have a combination of different methods. You've got a lot of tools, different techniques, and they're all, depending on what you want to do, they're needed. You have the analysis, you got statistics, you have visualization, you have some automatic analysis that we'll do today. You need to mine some data, because that's what you're getting from your analysis. And then you have the measurement itself. You can do sampling, you can do instrumentation, you can just look at the profiles, or you can do tracing too. On the instrumentation side, you can do it directly to the source code, you can do it on the binary itself, you can do it manually if you need to, which is hard, but you could. You can do it automatically, which is what we'll be doing today. And so finally, to go through the typical procedure, it's the first thing you need to do is to ask yourself, do I really have a performance problem? You need to look at timings, look at speed ups, look at scalability measurements. And for your own science stuff, are you happy with the amount of time it takes? Typically the answer is no, but if you are, then you don't really have a problem, right? If you're satisfied with how much time it takes, and you can get the results that you want, then that's fine. But if you do, then the next thing is to look at your speed up. If you're going to apply for resources in something like Prace, if your speed up is very, very poor, then you probably won't get resources, right? So what do I mean by speed up? I mean that when you double the number of cores, how much faster is your application, or how does your, depending on whether you're talking about a bigger problem size or the actual same data set, what's the speed up like? If it's really poor, so if you double the number of processors and you only get a 20% improvement in your speed, then your scaling is very poor, and you probably won't get access to resources because you won't efficiently use them. Your code is not built that way. So then you have to look at these speed ups, and the scalability is how does the problem size change, and how does that affect my performance. The next thing you need to think about is, well, what is the actual key bottleneck? Is it the computation? Is it the communication? Is it my OpenMP? Something like that. And then basically, the flat profiling can help you a little bit here. We'll take a look at that later on. So is it MPI, is it OpenMP, is it flat profiling? If there are other factors involved, maybe like the GPU stuff, then that's something else you'll have to look at. We won't do that today. Where is the key bottleneck? That's when it becomes interesting to do the call path profiling to see exactly where is your problem in your code. And then you can look at some detailed blocks inside the code as well. And then why is it there? There's some things you can do regards this. You can actually look at hardware counters. So do I have a memory problem? For example, tomorrow we'll see a little bit that OpenMP can kick up some really annoying memory problems that are very well hidden, but you can see them if you look at hardware counters. And then, I mean, you can see them straight away because they affect your performance, but you can figure out why they're there from the hardware counters. But there are some really good tools to help you with that anyway. Then you can also do traces. So if you've got the MPI stuff, you can trace things and see exactly where your problems are and why. We'll look at that again tomorrow too. And to try, you don't want to trace everything. So the idea is to find your bottleneck and trace that particular region, because you know that the trace files are going to be huge. And if you're only interested in the little region, then you don't want to look at everything. You only want to look at this particular piece. And the question is like, does the code have scalability problems? So can it scale? Then you want to look at things like, does it have a load imbalance problem? Is there like one thread or one process that's really busy and the other ones are not doing so much? And does that move around? You can actually see that in climate models a lot, because especially if they do something like chemistry, because the sun rotates around the earth. So basically you have a lot of chemistry going on in particular regions at different times of the day. And the imbalance rotates around the earth as you go around. So you can actually visualize things like this and see that at some point in time, some processes are really busy and other ones are not doing very much. Right? So it's a typical thing that you see where you have some effect actually from the physics problem itself. And then you can compare profiles at various sizes, of course, and look at them function by function to see where exactly your scalability problem is really coming from. And that's the end of this presentation. So I think we did pretty well on time there. Yeah. So we have about 50 minutes or an hour. I don't want to give you a break because we really don't have much time, and I actually have quite a bit to get through. I hope you don't mind. If you have any questions, just ask. Otherwise, I'm going to start into the hands-on. The idea of that tutorial, that lecture was just... sorry. The idea... That was exactly right. That's surprising. The idea of that one is just give you an introduction to the general idea. We're now going to do something very practical. We're going to look at a tool that's developed in Jülich. I have to give you a little introduction to it to give you an idea about it before we start, but then I'm going to try and run really quickly through this, and so we actually just get straight into the hands-on side of it. This tool is called Scalaska. It can do a lot of things, and we'll look at some of the different things it can do. The one we're going to take a quick look at today is this automatic trace analysis. So rather than you physically looking at the trace files yourself, it can do some analysis for you and tell you where your problems are. We'll see the type of problems that there are in a minute. Again, this comes from the VIA HPS and the Scalaska team at Jülich. So the idea this time around is that we're doing some kind of an automatic search for inefficient behavior. That's basically what we're doing here. Scalaska will try and do that for you. It'll classify the behavior in some way. It'll say it's of this type, it's of that type, and then it'll tell you how important it is. If it doesn't take up significant amount of time, it's not really important, right? So even if it's inefficient behavior, if it doesn't happen very often, it doesn't have a big impact on your execution time, then you shouldn't really care about it too much. So basically, you'll have this low-level event trace that you're doing. That'll be done. So these big files, it will do some automatic analysis for you, and it will give you a high-level result, right? And so that will allow you to see where it happened in the call path, what exactly it was, and when it actually happened. The nice thing about it is that it's guaranteed to cover the entire event trace because it's all automatic. It just data mines them basically. It's much quicker than actually doing it by hand, obviously. And then they have this parallel replay basically where they can replay the communication patterns and things like that happened. So it exploits the memory and the processors that you have when you run your application as well. The project itself, it started in 2006. It was a follow-up to another project called Kojak back in 1998. Now it's being jointly developed by ULIC and the German Research School for Simulation Sciences, also partially based in ULIC. The objective of the project is to do scalable performance analysis. Scalable is the really important word here. So this code specifically targets the really large-scale parallel applications. It's looking on the ones that run on the big machines like the Blue Gene machines or the Cray XTs that can have up to 1 million or more processors or threads. The latest release, it maybe not be the latest release anymore, but it's the one we're using today. That's version 2, and it uses something called SCORE-P, which actually does the instrumentation side of things. It's open source. You can download it if you want. It's pretty portable. It works on many systems. We'll be using it on a cluster today, but it works in the Blue Gene, on the Crays, and the other types of machines. It uses this thing called SCORE-P to actually do the instrumentation. So the nice thing about SCORE-P is it'll work with a lot of tools on the other end. And so basically it does the instrumentation, but many tools can interpret the results, which can be quite useful. So the Scalaska basically then is more focused on the trace-based side of things. Has some common data formats that you don't really care about. The current limitations on it, I mean, things develop all the time, so it can't do everything. At the moment, it doesn't do nested OpenMP parallelism, so threads coming from threads, and it can't handle these trace files that actually have CUDA events inside. So at the moment, it doesn't support CUDA or these GPUs in general, but it will in the future. There are other tools that do support the CUDA events, and they exist already. The typical workflow is that we have our source code, we want to instrument it, and it gets compiled and linked. This happens in one step. At the end, we have an instrumented executable. So then when we run, we have the target application, which is linked to the measurement library and maybe some hardware counters as well. We run the application, and on the other side, then we're going to get our summary report. We take a look at the summary report, and we can do that through this visual browser that we're going to use today. So you can see what's the problem that I have, exactly where does it occur in the program, and which process is it. In this case, I know it's a little bit hard to see it that distance, right? But this is to do with synchronization. It's a wait. It's an OpenMP clause, and you can see that it's this particular thread from this set of 4 that's doing all the waiting. So you can look at that particular problem.
Sorry?
Yeah.
To make this analysis, you have to prepare your code.
I'll show you an example of how to do that today. It's not so difficult. It depends on how complicated the application is. So if you develop the code yourself, it'll probably be very straightforward for you to do it. If you're using somebody else's application, like a big climate model or something like that involves hundreds of thousands of lines of code or something, things can get a bit more complicated. But if it's your own application, it should be fairly painless. So then we can look at this summary report, and then we go back and do more measurements. This time around, we're interested in the tracing. Okay, we do some local event traces. We can search through the trace files and look for these wait states and things like that, and then we can get a report on the wait states. And basically, that's what Scalaska does. It'll do the tracing for you. It'll do an automatic search, and it'll create a report that you can read on the other side. So here's an example of the kind of things that it can capture. In this case, it's an MPI all reduce. So basically, in this case, the time spent waiting in front of the synchronizing call until all the processes have to reach the call. So basically, any time before they all reach the call, in this case, this is the last one to arrive, is waiting time. Right? So this applies to all these collective communicators like MPI all gather V, all to all, and so on and so on. You can also have late broadcasts. So broadcasts come from a particular processor and then goes to everybody else. And if the other processes come to the broadcast statement first, then they have to wait for somebody to send them information. So basically, this time before the root sends the broadcast is waiting time for these other processes. For the case of this process, it didn't have to wait, it was already broadcast, but these other two had to wait, so that's also wait time. You can also have a late sender. So basically, you have a receive statement that's been posted, information hasn't been sent, and it has to wait until the send comes. So it's a blocking and receive in this case, but it doesn't have to be exclusively a blocking and receive. You can have a late sender in the case of this blocking statements, in the case of a non-blocking statement, because this is a blocking and receive on this side, but it also happens for non-blocking on both sides. So in this case, this particular case, you have a non-blocking send, non-blocking receive, but this posted the wait statement before the send had started. So we still have wait time here.
So if the wait time is long, you have to find a way to do something to shorten it.
Yeah. Or yeah, basically, yeah. I mean, the application will tell you if you have long waiting times, and then you have to think about why they're there. It could be to do with this kind of your scalability problems, the fact that one process is doing much more than another one, which means it's far behind. So they're not so, the work is not so well distributed or something like that. And there's not much you can do about that. These non-blocking statements won't help you too much with the fact that you're not very well distributed. So it applies to, like I said, it applies to blocking and non-blocking communication. So now we're finally on to the hands-on side of things. We're going to use an example. It's actually a benchmark from the US. The first thing I want you to do, and I want you to be really careful here. So how many of you are actually on Linux systems? Because what's going to happen is I'm going to need this is going to be a little bit graphical. So it's going to be a little bit slow, maybe, and that's why I want you to use these commands here when you're connecting by SSH. So what they mean is that it's a trusted connection, so that it doesn't do some encryption stuff, and then it's compressed as well. So it's capital Y, capital C, so it'll squeeze down the graphic stuff to make it work a little bit faster. For me, it's functional. It worked when I tried it yesterday. It's a little bit slow on the responsiveness side of things. But basically, if you've got a Windows machine and you haven't already set up the X environment, then it's too complicated to do it right now. So if you have a Windows machine, I suggest you would sit beside somebody who has a Linux machine so you can see what's going on. So I don't know if you want to move around on the basis of that. The people who have a Linux machine, could you stick up your hands again so people can maybe shift around a little bit? If you have the X environment, and if you have that, that's fine. So if you've already set up the X environment on your Windows system, then you can go ahead. But if you haven't, we're not going to go through it now. It's too complicated. So okay, so just make sure and connect with these particular commands with the capital Y and the capital C. You've already been through this whole module situation, so I'm just going to brush over it really quickly. You know there's a lot of modules on the machine. You can list the ones you have currently loaded. There's probably, when you log in, there's two. It's just Torque and Maui. They actually manage the queue and the resources themselves, so they're loaded by default. Everything else you can see by module avail. What we're interested in is this Go MPI module. So basically that's just GCC and OpenMPI stuck together. Okay, so they're the two that we're going to load. So that particular module is the one we're interested in because that's what we're going to use to compile. The actual source code for the tutorials, it's available in the /temp directory on Euclid. Right, so basically you want to copy the whole directory onto there's a dot at the end here, don't miss that. So that means copy it to your local space, wherever that might be. And then we're going to go inside. So this Prace Winter Workshop directory has everything for tomorrow's hands-on as well. The particular one that we're interested in is Scalaska. That's what we're going to do today. Inside you'll find a directory called mpv blah blah blah, and just go inside there. The slides are online, so if I move forward and you're looking for something, just take them from the slides, okay? Okay, we don't have it, but in this case, when they're available, you should always try and use the parallel file system such as $work, okay? In this case, you don't have it, but typically on a Prace system, this is just a training cluster. On a typical system, you will have a fast parallel file system. A lot of places call them $work. Okay, so the benchmark suite is what we're using. You don't need to know much about it. It's actually written in Fortran 77. Has some. If you do an ls inside, you'll see it has some files. That's fine. Don't care about those either. The subdirectories have all the source code. You don't mind. It's already been all configured for the tutorial, so really you don't have to worry about this stuff too much. It should more or less just work for you, hopefully. If you type make, if you go into the directory and type make, this is what you should get back. You can try it and let me know. You see, yeah, I made a. So you need to load a. I probably left a. Well, we'll come to that in a second. But basically, ScoreP is a module, so you need to load the ScoreP module. You can. I'll do it in a second. But basically, I left a comment in there that I shouldn't have left in. That's okay. Well, I'll do it. I'll do it here too. So. So hopefully you can see my screen. If you can't, shout and. Okay. Okay, so I'm going to copy what you're doing here. So basically, let's make this a bit bigger. So we'll go into. We're in the space, we go into the Scalaska, and then the subdirectory. And now if I type make, it should complain, which it does. Oh, well, it doesn't complain, it gives me some information. Okay, I'll fix that for you now.
I don't know, I'm not sure it's going to work.
Okay, so I have the same problem as you, the ScoreP one. I didn't load the Go MPI, okay? So probably the reason is if I load the ScoreP directly. How do we do it? I forgot to say load. Load score. So there are a couple of different versions of ScoreP. The Go MPI module you probably loaded is 1.6.10 instead of 1.4.10. That's the problem you're seeing now. So if I just load the ScoreP module, it'll automatically load the Go MPI one as well. So if you want to unload the module, you can do the module unload, or you can just do a module purge, which will get rid of everything. But that might be a problem in a minute.
Go MPI should be unloaded?
Huh?
Go MPI should be unloaded first?
Yeah, because the default one will be 1.6.10, which is not the... And so now basically, if I type make... sorry, I have to do this. Yeah. So I loaded the ScoreP module.
Can you go back to the module name?
Yeah. So basically, do you know tab completion, right? So you can do this yourselves. If you go to module load, capital S, and just start pressing tab, it'll give you all the options with the capital S. Right? You press so ScoreP, it'll give you all the options. I've already loaded the ScoreP, the Go MPI one, so that's why it says there's only one option left. I don't want to do that, so because it can conflict anyway.
So just to log in, but via
SSH, yeah?
yeah, via SSH on PuTTY. It seems like you don't really recommend that because it's too complicated to get it.
It's because in a minute we'll be doing graphical stuff. So to do this command line things, no problem. I mean, you can do it, but when we come to actually looking at a graphical thing, it's not going to work. Yeah. Yeah. Sorry, say that again? Sorry, I couldn't hear you. Could you say it again?
How would they be able to? I mean, one quick way to verify if X is volume, but X term is stalled, but sometimes it stalls anyway.
Yeah, it could be the Wi-Fi connection here or something like that. I mean, we might run into Wi-Fi problems when everyone starts doing graphical things. We'll see what happens. Yeah. Okay, so.
I can
have it, so it's already loaded. You have a currently loaded module. You go MPI one.
And it did conflict with OpenAPI. Maybe something like
Do module list and then see what's loaded. Oh, so you have a lot of stuff loaded here, okay? So 1410, that's okay. So it shouldn't conflict with anything else.
I think the conflict
Did you load that separately?
yeah.
Just do a module purge. And then just go module purge. No, module purge will just dump everything out. It just means that actually I'm going to do it first because you need these Torque and Maui ones.
So I've done the first.
So it's unloaded everything now, and then we want to do Torque and Maui because they control the queues. And then we want to score. What you go and then go on. Okay, let's anyway, we're kind of jumping ahead a little bit because we don't need to make it quite yet. As you saw in the output, it asked you to make it in a particular way. Make BTZ, class B, prox number of 4, for example, right? That's what we're going to do. And once you have the scorp thing loaded, it will create the executable in the bin.scorp directory. I think that's on the next slide. What does it actually do? The code doesn't really matter. It's just Navier strokes. It performs about 200 time steps in Fortran using Fortran 77. It has MPI and OpenMP in combination. It should take about 30 seconds, actually less on Euclid. At least it did for me yesterday. There's a little bit of a problem that because I didn't pay attention last night when I played with it. I'll need you to edit a file, a particular file. So basically, if we go to there's a config directory. So if we go to vi config, it's called make.def. So in the config directory is a file called make.def. We go look inside, and you see that there's a lot of these MPI F77 statements. Basically, what they say is which MPI Fortran compiler should I use? The default one is just MPI F77. You can see it on this line. So this is line 30. Now, last night I uncommented the score P line. So this would have been a little bit later in the tutorial. So we're going to have to undo it a little bit. So basically, I just want you to put back in the comment here. So basically, comment out that line. So insert the hash in there. Okay.
Which one to open instead?
Just comment out that line, and the default is above it. You'll see it. So you don't if you just comment out that line, it'll work.
And exit the file.
And that's it. All I want you to do is to comment out that line. So it's just line. It's line 41.
Okay.
Config make.def. Just insert the comment statement, and that's all I want from there. And so basically, if we go back up and do the make statement again, so we're back in the root directory. If we do the make statement again, this time we don't have the score P problem because it doesn't need it anymore.
Make without any flags?
Huh?
Just make?
No, you need the arguments again, these ones. But it's exactly the same command as before, make btz, blah, blah, blah. You can just scroll up. And now if you do it this time, you'll see that there's a bin directory. And if you go into the bin directory, you'll see the executable. So basically, for the different tools, it creates different bin directories. So accidentally, we created the score P one already. That's fine. We'll use it in a minute anyway. The other one was the bin directory, which is just a vanilla executable, no tools involved at all. Okay. We're going to run that executable. If you're inside in the directory, has everyone managed to make the bin?
No, can you
Here's what I did. So basically, if you look at the last commands that I ran, I edited the config file, commented at line 41, and then I just was back in the directory that I wanted to be in, and just did the make again, and then that created a directory called bin, which I'm now going to go inside. Where are you trying to put them, actually? Because they're world readable, so you should. Oh, you're trying to take them from my home directory. Take them from /temp. They are in my home directory, but that's not where you're copying them from. You're copying them from /temp. Ah, sorry, this is wrong slide. Fix that. Before the slash. Okay, rid of that. You have permission to link to your own directory. Oh, there is no work. There is no work. So, are you using an old file? Or this file shouldn't be there anymore. This is if you go to the main presentation, so this correct information is in this main presentation. I asked to take it up this morning, but yeah, maybe I should have done that a week ago. If you can find it again, it's the Scholastic presentation. And in there, it should be correct, I think. Just comment it out, that's all you need to do. Yeah. And then if you just do the make again, if you create a new directory called bin. Okay. So
we did the make and we have the bin file, but it says I don't have the full blah blah blah.
what's the error? Let me clean up things a little bit for you. I think your environment is messed up. So let's just do So basically, what would be enough is you would need to manage the queue, store the resources that's known, just need score P. That'll give you every dependency. Score P. No, sure. Now try it again and score. Okay, yeah, we're starting to run short in time. We won't even get to look at the pictures. Maybe what I'll do here is, because we only have like, what is it, 15 minutes left or something like that?
20 minutes.
Right, so maybe just follow my lead, okay? Or just follow what I'm doing on the screen up here. And then in the tutorial, you can try to do it yourself another time or something like that, because I just don't think we'll have enough time to get through everything. Okay, so so the first thing I want to do is copy, I have some job scripts here that'll submit jobs to the queue. We got some special ones for Euclid. You can see what they are inside there. I have a couple of special ones for ScoreP that we're going to use in a minute. The one we're interested in now is this run.qsub. That'll just run the command. Sorry, I forgot to give it destination. That's here. So then I can just do qsub to submit a job, run.qsub. It's been submitted, okay? We can see, oh, somebody else is running a job too. Who's that?
Somebody's job is stuck for 1 hour.
Who's U62?
His whole job is stuck.
4304 is my job, yeah. But it is Scorpio.
Yeah, maybe. I'm a bit surprised it shouldn't be. It's with no filter file. Yeah. So the thing. Well, that was something I was going to come to in a minute, right? So this overhead of. Okay, you jumped a bit too far ahead. My job should be finished by now, though. So my job is finished. In total, it took, where are we? 20 seconds. So it took about 20 seconds runtime. All right. So that was my one. The next thing we want to do some performance analysis on that. Now, what we've done. Huh? You can run it. You can run it if you want. It should only take 20 seconds. It's the next one that's going to take time. So the one you just tried. So I may not do it actually. So basically, if we go into the bin score P one, so we've already created this score P instrumented executable already. We can also run that, so we can copy all the. What am I doing? Sorry. So we go to the submit scripts, again job scripts, Euclid, and then you can see there's a couple in here. We got the different score P ones. I could run this one. The point of running it, I won't do it because it'll take a bit of time and take up space in the queue. The point of running it was to show you that the performance and this performance measure has a big impact. So it took 20 seconds to run the code vanilla, okay, with no instrumentation at all. It took 20 seconds to run it vanilla with no instrumentation. If I run it without giving it a filter file in score P, it'll take about, how long did it take it for you? 10 minutes or something like that? Or yeah, it takes about 10 minutes to run, right? Once I instrument it, right? That seems huge, right? But it's actually for very simple reasons. It's because there's a couple of routines inside the code that get called many times. And it kills the performance when we do the performance analysis, because it's recording every single event for these routines. In, out, in, out, in, out, in, out. And so it slows things down an awful lot. Now there's something called filters that you can use to improve that. So basically what we'll do is we'll copy the filter here. Got the destination again. Okay. So we submit the job, and while it's running, I'll show you what's inside. So basically, we'll submit this job, and then let's have a look at what's inside. So basically, this is a job script. It looks complicated maybe, but it's not. Just has some variables inside. We load the modules that we're interested in, the Scholastica one, Score P. it sets some variables, make sure we know the number of threads and this particular variable which disables load balancing. Doesn't really matter. Here's the filtering file. We'll take a look at what's inside there in a minute. There's an experiment directory. Anyway, this is just a submission file that I created for you. You can have a look inside and try and figure out what things mean. It doesn't really matter for our job, for what we're doing today. We had to use the scan statement because, well, maybe I'll come to that in a second. But basically, yeah, I should really show you on the slides where we are. So the job is running anyway now. So this was the original job, right? The bin one that took about 20 seconds. In our case, it took 20 seconds. That's the general output that came from inside it. There are a lot of VI HPS tools. We only have a subset on Euclid at the moment. We've already edited this config.def. The idea here was to allow us to use the particular tool that we were interested in. In our case, we did it a little bit too early, but it doesn't matter. So here you have the file that we already edited. In this case, we should have been removing this file instead of adding it. I just accidentally left it inside, so we had to do it the other way around. And now we do the actual hands-on. This is where I should talk a little bit about the Scalaska things themselves. So you have Scalaska minus instrument, which does the instrumentation. In our case, we're actually going to use score P, okay? Because this instrument is a little bit outdated now. So we use score P. That's why we edited that particular line in the file to allow for this instrumentation score P. At the runtime, you can either use Scalaska minus analyze, which is the long form, or scan, which is the statement that's in the submission script. And then when we come to look at things on the other side, it can either be Scalaska minus examine, or you can just use the short form, which is square. Okay, yeah, it just says here that this minus instrument is depreciated, and we suggest you use the score P directly, and that's what we've done in our case. Okay, so scan is the one that's in the file now at the moment. So scan basically means when we're running. So if we go back to our thing, you can see the scan statement here. I had to be a little bit sneaky in a way, but it gives you hints about how to do this properly. To give all the arguments that you need to give to MPI run, they have to be enclosed in little comments. Okay, so it's a feature, or I don't know. It warns you about it. So basically, if it sees things that it doesn't like, it'll warn you that you may need to do this, and you do, typically. You can take a look at the job submission file. You don't need to know about this now. If you're really interested, the information is there. So you can try and fail on your own, and the solution is there. Okay. So we'll do that now in 1 second. I just want to show you the type of information that's inside in the filter file. And so basically, so the filter file contains some routines that we tell it to ignore, right? So there's a what's called a summary file that contains information about these are the user routines that are inside. We can basically tell it to ignore everything that looks like this. So when you have your summary file, there are some routines that get called millions and maybe hundreds of millions of times, and they're the ones you want to ignore. And this is the place that you would put the files that you want to ignore. I'm not going to go too much into detail about everything today because we really just don't have time, okay? So if you really are interested in these tools, these guys have dedicated workshops around Europe a couple of times a year, right? And they're available within Prace. So if you really, really want to use these tools, then this is not the right form to do it. You need to go to a special workshop for them, okay? Because I just don't have time to go into all the details of everything here. So like somewhere else is the place to go. But I want to give you an example that we can actually look at today, all right? Okay, so we have our little directory here that got created when we ran the job. We can have a look at the output just to see how long did it take. So here's the output from the job. Okay. Here's some statements here saying, hey, I'm doing the scan now and everything, right? Some information from score P, etc. It does the same thing with its time steps, blah, blah, blah. at the end we can see there was still an impact. It took a little bit longer. To be really sure how much that impact is, I'd have to do a number of runs, okay? Maybe 10 runs and see exactly what was the overhead of doing the measurement. Was it like, it looks like it might be about 10%, maybe less. Typically it's a little bit, you can get it down to a little bit less than that. Okay, but the overhead was maybe about 10% to do the measurements. I can live with that, right? And that's the end of the job. So now we're going to come to the visual things. Alright, so we've done our scanning. And the next one is the visual things, the square. We're going to look at some analysis. So the idea was to scan configures some of the score P stuff to do the measurements. Also include some consistency checks. For the tracing, we'll do it afterwards. But I'll just take a quick... We're not going to have time to do tracing, but we'll try. So square is the command. I haven't loaded the Scalaska module, so I have to load it now. Okay, so now that's loaded. Square P, and you can leave you basically give it the whole directory. Give it a second, and we should get some. There we go. Like I say, it's not fantastically fast, so it's not going to be instantaneous, everything that I do here, but it will give you some interesting information. Alright, so basically this is our flat profile over here. We see on the top the amount of time that it's taken. You can look at different visits and things like that, synchronization, MPI. The one that we're interested in is the time, where time was spent on the top. We're going to look inside. So we open it out a little bit. Sorry, but it'll take a second. So we see we spent most of it on execution, some tiny bit of time on idle threads. As I said before, this is a benchmark, so it doesn't have performance problems, right? So we're not going to see, in the case of your application, things could be very different, right? If we look inside the execution time, you can see that most of it was spent on actual execution. There was a tiny bit of time spent on MPI. There was about 29 seconds spent on OpenMP related stuff. On the execution side, if we click on the execution, we can actually see where the time was spent. Where was it doing all this executing? So if we go into the middle panel, we can open out the functions and everything. So we can see we got the main function. We can open that out. We can see it spent, no time and all this stuff, and basically everything in something called iteration. Sounds a bit suspicious, right? So we go inside, something that gets iterated over, obviously. If we open that up, we can see it's spending all its time in this function now. We break that down. And now we'll see that it basically splits it. Remember, it's a three-dimensional problem. There's something to do with computing a right-hand side here. And then it has all the three different functions, right? So X, Y, and Z for the three different dimensions that we have. So we can click on that. And then we can actually look on the right. We have the actual layout of the processes on the machine. So we can see that we had two nodes, E04 and E03. If we open those out, we can see we had two ranks. And there was 4 threads per rank. So we can actually see the threads. And then you can see the layout of the work. 6, 6, 6. And then the last thread did a little bit less work than everybody else. Okay? This is to do with the distribution of the problem, probably with the way the OpenMP threads did the scheduling or something like that. It'll actually give you hints on that type of stuff as well. But that's basically it. Like I say, we don't have time to go through everything that you can do here. But that's basically it. You can look at where you spend time. You could do exactly the same thing with the MPI. We could do that. Well, let's do it with OpenMP because that's the one where we have a problem. And then you can see here, it's exactly the same thing. We got the 29. That's all in the same region here. And you can see that the problem is this last OpenMP thread. That's the one that's not doing as much work as the other 3. Right? And that's where you get your waiting times. But again, you have to consider the amount involved. This is at the 10% level, right? So execution is 330. OpenMP is only 10%, 30. Don't need to worry about it too much, to be honest. It's probably not worth the effort, right? If it was a big problem, the split would be much more defined. If this was 100 and this was 200, then you will need to spend time here and figure out what the problem is, right? Same with the MPI stuff. If there's more time there, then it's worth paying the effort there. But really, in this case, it would have been the execution. That's the one where you would have said, this is the place where I need to spend my time. Then you would have looked at, where is the execution problem? And if I was looking to do performance improvement, I'd go, well, I have to do this one, and this one. They all do the same thing, more or less, just in a different dimension. So really, if I improve something here, I fix all three.
You have the result is score P.
Sorry?
The results you show it with score P.
The instrumentation comes from score P. This visualization is from, it just interprets the information, yeah?
I did the same with score P. In my job, the benchmark
Yeah.
idle threads have 3,000.
Yeah, so in your case, you did it without a filter file. Remember, you had the filter file, so your the execution time. So this is the problem, right, of not comparing the time to the initial time. So the initial one took 20 seconds. In your case, it took, what was it, like 10 minutes, right? So obviously there's something wrong. That overhead is from not using a filter file. So with my case, I use the filter file, I get the real results. In your case, you get the wrong results because of the filter file. So the first thing to do is make sure that the overhead is not too much. Right? So 10%, okay, we can live with that. Above that, things get a bit dangerous because now you're getting information that's not actually true. That isn't really relevant to you. It's all coming from the measurement process, not from the application.
Where is the filter file?
There's another submission job submission. So it says you submitted the one with score P. There's another one that says with filter, and then you can have a look in there. Yeah.
What does the OpenMP section include?
So yeah, you can do this again yourself separately, but basically it more or less spends time looking at the synchronization. So how much time was it spent waiting for everybody to come back together? Like it split the processes out. How long is one of the processes idle, waiting for everybody else to come back together? And basically what happens in this case is that one of the threads just doesn't get the same amount of work as everyone else, so he spends more time waiting. He's on the end. Right? So basically when you cut up an array, he doesn't get the little piece at the end. Right? He's the one who sits there doing nothing, only has a piece of the work that everybody else has. So, okay.
How could you have shared your job more uniformly between the threads?
You could do
the amount of threads to the size of the array.
You could do something like that, or you can dynamically do give the threads work, right? So they actually, maybe I should bring it up. It actually gives you hints on this stuff, right? So you can actually give a hint. I think it'll work better with the tracing. I'm not sure if it gives you the hint now. You might have to do the tracing to get the hint, but I think maybe it does. So basically we can look at, if we go down inside, we got the idle, the execution time. Idle threads, right? So we can do a right click on the idle threads. It'll take a second. And then we can do online description. What does that mean, okay? So what do all these things mean? If you just right click, you can get the information on what each thing might mean. And so basically it'll tell you here what the idle time is. It'll give you a little diagnosis on what that means. So basically all the information is in there. Basically if you right click, you can actually look at what does that actually mean, and then it'll even give you hints on how do I fix it. And so one of the things that the limited parallelism, I think. Sorry, like I said, the graphical stuff is a little bit slow. Come on. So I think it'll come if I go inside the end. Yeah, unfortunately I won't have time to do the tracing, but basically there is a job submission file in there that includes the tracing as well. You can run the same thing, and if you do this scan or this square on that tracing file, you get different information about late senders and things like that. It's in the presentation at the end. If you just kind of keep going through it, you'll get there. sorry, we just don't have time for it today. And tomorrow we move on to something else. Like I say, it's a kind of a big subject area. It's really, really difficult to try and squeeze it down into something you can actually handle in 2 hours. So I can't do it. I've done my best. Like I say, the stuff is in the tutorial. The sample code is on the website. Try and do it on your own. I don't know when you're going to find time, and I leave tomorrow. So if you have any questions, you're in a hurry.
1 month from now, you'll get